To Jellyverse channel. Make sure you do well to subscribe to the channel and also comment and like. This video we are going to talk about organic chemistry, and the course code of the course is Chem 114. It is being presented by Jellyverse, and the course is about introduction to organic chemistry, that is compounds of life. When we are talking about organic chemistry, what does organic chemistry means? What does it entails? So let's move straight into the course. Organic chemistry is the study of carbon compounds and their reactions that it undergoes. So carbon compounds, a compound that contains carbons is classified as organic chemistry. But usually in chemistry, we have a lot of exceptions. The same thing applies to organic chemistry. There are some of the compounds that they do contain carbons in them, but yet they are not classified as organic compounds. Example of these compounds are carbonates, cyanides, and also oxides of carbons. Example is what you are seeing here. Sodium carbonate, even though it contains carbon in them, it is still not an organic compound. The same thing applies to cyanide. You are seeing potassium cyanide here. This is a carbon with atom combining with nitrogen in the form of a triple bond. That's a cyanide ion. Now, this compound is not classified as an organic compound, even though it contains carbon in them. The same thing applies to oxides of carbon. A typical example of the oxides of carbon is the carbon dioxide. Carbon dioxide is a carbon bonded to two oxygen. We have carbon monoxide too as well. These sets of compounds that have been listed as an example are not organic compounds, even though they contain carbon in them. Now, over 60 million of carbon containing compounds are known. And now let's look at the group in which we are going to find carbon. Now, carbon is in group 4. And when we are saying group 4, these are elements that can bond to themselves. As for group 4 elements, they can form a bond with themselves. For that matter, they exhibit the property called catenation. So catenation is just a term that describes the ability of an atom to form a bond with itself. Carbon is in group 4. Group 4 element is not only carbon. We are having silicon, we are having germanium, we are having tin, we are having lead. Sorry. But there is something that you should know. How carbon behaves is different from how silicon behaves. How silicon behaves is also different from germanium, as well as the others like tin and lead. Now let's look at the reasons. In terms of catenation, in terms of the ability of group 4 elements to form a bond with itself, it decreases whilst you are moving down the group. For instance, carbon is the most active element in group 4 that can involve in catenation. Silicon, it can involve a catenation, but it is less as compared to carbon. So you see, whilst you are moving down the group, the catenation ability decreases, and there is a reason for that. So catenation, this is the definition. Catenation is the ability of a compound or an element to form covalent bonds with atoms of the same element. Carbon forming a bond with carbon. We are using covalent because when an atom forms a bond with itself, its electronegativity difference is negligible. For that matter, they tend to share the bond. That's why we are using covalent. Now let's look at examples of some catenation. Catenation include branched. So we are having branched catenation where the carbon is forming a branched chain. We are having a straight chain or a carbon chain. As you can see here, carbon bonded to carbon, bonded to carbon, bonded to carbon. And we are having catenation in a form of ring where the carbon can form a ring, especially cyclohexane. Now with this, let's move on to the trends in catenation like I said earlier in the previous slides. For the ability of catenation in group 4, like I said, carbon is the most active element that can catenate, followed by silicon, followed by germanium. So this means down the group, the catenation ability decreases. And the reason is that the atomic size increases. When the atomic size increases, let me use a pen to illustrate what I mean. If you are considering this one to be carbon, we expect silicon to be much bigger as compared to carbon, and we expect germanium to be a little bit bigger compared to silicon. So you see, whilst you are increasing down the group, the atomic size increases. And when the atomic size increases, the bond becomes weaker because it lengthens or it becomes longer. And the longer the bond, the weaker the bond. So you could see that when carbon forms a bond with another carbon, the bond between this carbon and this carbon, the length is short. So the shorter the length, the stronger the bond. For that matter, the stronger the catenation ability. But if the atomic size increases, then this means that the length of the bond also increases. And you're going to have your catenation becoming what? Decrease, because it's going to, the self-linking becomes less stable. If they are huge enough and they are forming a bond with itself, remember the bond length is going to be longer and it's going to be less stable. So carbon forms strongest bonds with itself and therefore it shows the greatest catenation. That is for carbon. Down the group, the catenation decreases. Now let's look at some reasons why carbon is unique. When we are saying carbon is unique, yes, it is unique because its catenation ability is a little bit stronger. The reason is that it is having 4 valence electrons. 4 valence electrons means in the outermost shell, this is the outermost shell because it is having only 2 energy levels, which is energy level 1 and energy level 2. In this energy level, in the excited state, you are going to have 4 unpaired electrons, meaning these 4 unpaired electrons are capable of forming 4 bonds. The number of valence electrons determines the number of bonds that a compound or an element can form. So right now, carbon have 4 but unpaired electrons in its ground state. So let's look at this particular electronic configuration, where in the ground state, this is what we are having, 1s2, and we are having 2s2. And in the p, which is the degenerate orbital, we are having 1 pair of electrons in the 2 orbitals, remaining the other one empty. So this is the empty orbital. Now in the excited state, one of the electrons that have been oppositely directed into 2s, one of it is being promoted into this particular orbital, and now we are going to have 4 unpaired electrons, which is 1, 2, 3, and 4 unpaired electrons. For that matter, for a compound or for a carbon to form a bond, it undergoes hybridization, a process called hybridization. And the hybridization is when you are going to have these orbitals containing each electron pair. The orbitals containing electrons that are having only one direction. For instance, this particular orbital, they all have only 1 electron each. These are the orbitals that are going to hybridize. Hybridize in an extent that they mix and they form a hybrid orbital. So if you are having 4 orbitals mixing, you are going to get 4 hybrid orbitals. So here you are going to have 4 of the sp3 hybridized orbitals. So let's look at geometry of carbon atoms. Carbon form different bonds. Carbon can form a single bond, carbon can form a double bond, carbon can form a triple bond. Now, when we are seeing the geometry of carbon, this means that in a particular bond of a carbon in a compound, how does it look like? What is the shape? So the geometry of a carbon atom depends on the number of groups that has been attached to. That's what we are referring to as the geometry. So the first one is tetrahedral geometry. That is when carbon has been bonded to 4 groups of atoms. And this shape is having a bond angle of 109.5 degrees. Usually, it's single bonds throughout. So you can see this particular structure. This is called methane. This is the simplest hydrocarbon. And here we are having carbon bonded to 4 different groups. You see, carbon has been bonded to hydrogen here, a hydrogen, a hydrogen, and a hydrogen. All these hydrogens are similar atoms. For that matter, all what you are seeing here is a single bond. So this is the geometry. So this is a tetrahedral geometry. And you could see the angle is what? 109.5. If you want to take the angle from this hydrogen to this hydrogen, it will also be 109.5. All the angles throughout is 109.5. Now let's look at the second geometry, which is the trigonal planar. The trigonal planar is when the carbon has been bonded to 3 atoms or groups. Usually the bond angle is equivalent to 120 degrees, as you can see here. And a typical example is 18. The simplest trigonal planar carbon is 18. So this is a structure for 18, where this is carbon. The carbon has been bonded to a hydrogen here, a hydrogen, a hydrogen, and a hydrogen, but there are two carbons. So if you are considering this carbon alone, this carbon has been bonded to three groups, which is this carbon is 1, this hydrogen is 2, and this hydrogen is 3. And you could see that if you want to find the angle from this particular side to this side is 120. The same as the angle from this particular side to this side is also 120. And the angle from this side to this side is also 120. So that's how come we are having the trigonal planar geometry. Now let's move on to the last part, which is linear. Carbon can also be linear. And a typical example of the compounds that have a linear geometry is ethane. Ethane is when you're having two carbons. It's a triple bond. And the other carbon, each carbon has been bonded to a single hydrogen. Now, let's look at the structure for ethane. This is carbon. This is also carbon. And now you're having three bonds here. And now you're having one hydrogen, one hydrogen. So this is to tell you that every day, keep it in mind that carbon can form maximum of 4 bonds per our level. Carbon can form maximum of 4 bonds. And you could see, if you want to check out for the angle of a straight line, it's 180 because this one is linear. So the angle from this side all the way to this side is 180. Alright, so now let's move on to the introduction of the whole organic chemistry course. Now, living organisms have been able to exchange matter and energy with their surrounding, right? They are also able to transform energy and matter into different forms. And you know that that's the capabilities of living organisms. Living organisms do grow, they do reproduce. They can also protect themselves from unwanted steam. So now let's see. This structure here, you could see a bee, you could see an ant. When a bee stings you, when an ant bites you, they releases an acid, and this is the simplest acid. That's what we are calling the formic acid. The simplest organic acid is the formic acid. So this is the introduction. Formic acid is the same thing as methanoic acid. So when we get to the place where we are actually going to talk about how to classify functional groups, you are going to realize that this particular formic acid falls under the functional group carboxylic acid groups. Now let's move on. As you can see, this one is a fruit, mango fruit. This is cassava, this is maize. They are all sugar. You could see in terms of sugar, it's the same thing as carbohydrates. So ethane, right? Let's look at some applications of chemistry here. If you are having unripe mangoes, right, you can add it to a ripening mango and place them in an ethylene or a rubber, right? And then you can store it in a cool, dry place for about a few days. And you're going to realize that it's going to release a particular stimuli, right? It's going to release a certain compounds that's going to help you to ripe exactly the days that you are expecting. This is to tell you that ethylene is a gas, right? Remember, we are having polyethylene. In polyethylene you can have ethylene. So ethylene is a gas that is produced and it is responsible for letting fruits ripe faster. So ripe fruits will release ethylene gas. So if you mix it with a ripening fruit like a ripening mango, it's going to release a gas. This gas is what we are referring to as the ethylene. So it will act on the mango that is unripe, and now it's going to speed up the ability for it to ripe. So a typical example is a tomato, right? A ripe tomato is placed with a green tomato in a sealed bag, and at the end of the day, it's going to help it to ripen faster. Now let's talk about macromolecules. When you are talking about macromolecules, living organisms survive because of large molecules called macromolecules. As you are a human being, you are surviving because you have macromolecules. We are having three main macromolecules. Macromolecules, when you are saying something is a macromolecule, it's a big or a huge molecule that has been formed from addition of smaller molecules. When you're having smaller molecules, plenty, and you join them together to form chain, it forms the bigger molecule called the macromolecule, as you can see here. So when you're adding these smaller molecules together, when you are joining them, we refer to that term as polymerization. So that's how come you are seeing the term here, polymerization. We are adding smaller molecules together to form a huge chain or a huge molecule. Macro means big or huge, so macromolecule is formed from polymerization of smaller molecules. Now, in terms of macromolecules, how we are surviving, we depend on three major macromolecules. The first one is proteins, and you've heard of proteins before. The second one is carbohydrates. The third one is nucleic acid. These macromolecules are the ones that are needed by human beings or living organisms for their control of cellular activities. If you want to think, if you want to talk, if you want to grow, you depend on these macromolecules. The second one is support and growth. If you want to survive, you depend on this. Also, to determine the structure and functions of organism. Remember, human beings are different from animals. So there is no way you are going to have a human being giving birth to an animal. All these things control the ability and the behavior of living organisms as well as the structure and functions of these organisms. Now let's talk about a term called metabolism. So metabolism is just the breaking down or building up of macromolecules. So if you are having these huge molecules like macromolecules like proteins, if you are building up a lot of proteins, or if you are breaking down a huge protein macromolecule, then you are referring to that term as a metabolism, or others call it metabolism, yes. So breaking down, remember this definition contains two things, breaking down or building up of macromolecules. So the breakdown of macromolecules is referred to as the catabolism, and the buildup of these macromolecules is referred to as anabolism. Now, if you are breaking down something, you release energy. But if you are building up, you require energy to build it. So that's how in biological systems it works. The energy needed is obtained from catabolic reactions. So I teach enzymology, and let me relate it with what I'm doing here. If you use catabolism process, you are breaking down, you release energy. This energy will then be used to build up the things that you want to actually build. So energy is not wasted. Whilst energy is being released, energy is being used. If you want to grow, your proteins needs to come together at a certain point so that it starts growing, so that it appears morphologically for you to see. All these things require energy. Where do we get this energy from? This energy is gotten from the breakdown of macromolecules. So the summary here is catabolism is equal to breakdown of macromolecules to release energy. Anabolism, you are using energy because you are building up something, you are building up molecules. Now let's look at protein. Protein are macromolecules. We all know proteins. Proteins are polymers, right? Meaning they are formed from smaller units coming together to give you that protein. And the smaller units of these proteins are what we refer to as amino acids. Amino acids are the smaller unit that comes together to give you your proteins. So this is a typical example of an amino acid unit. So the first round one is called glycine. Second one is called proline. All these things are examples of amino acid, and they have come together to form a very long chain. As you can see, this is a very long chain, and this is called protein. We are not moving into details because we are talking about organic chemistry, but this is the introductory part of it. Now, in terms of carbohydrates, carbohydrates are also molecular compounds. Remember, carbohydrates are made up of carbon, hydrogen, and oxygen. And we are saying something is hydrates, more like water. Water is H2O. and carbon, so carbohydrate, meaning carbon with H2O. So they serve mainly as the biological molecules, and they serve as a source of energy. If you need energy right now, you have to eat. The amount of food that you take in is carbohydrate or protein. It releases energy. So example is the glucose. If you take in glucose, it gives you a lot of energy. If you take in sucrose, it gives you a lot of energy. So carbohydrates are generally classified as sugars. Now that is to tell you we are having classes of carbohydrates. So if you can't say sugar, say saccharide. Saccharide is the same thing as sugar in biochemistry. So when you are saying something is monosaccharide, meaning one sugar. So one sugar unit. Monosaccharide meaning they are the sugars that are made up of only one sugar unit. Example is the glucose. We are saying disaccharide. Disaccharide are carbohydrates that are made up of two sugar units. We are having trisaccharide. We are having polysaccharide. So here you could see that this is monosaccharide. Monosaccharide example is the glucose. You could see only one sugar unit. This is glucose, only one sugar unit. But in sucrose, we are seeing 1 and 2. So meaning this is a disaccharide, two sugars. We are having oligosaccharide. Oligosaccharide means, oligo means few and saccharide means sugar. So this means few sugar units. And we are having polysaccharide. Polysaccharide means a lot of sugar units that have come together. Now, let's talk about the last one, which is nucleic acid. When we are talking about nucleic acid generally is about DNA and RNA. And you know the difference between DNA and RNA. They are essential biological molecules because if you want to think, if you want to transmit your genetic information, if you want to control your cellular activities, everything depends on these nucleic acids. So nucleic acids, they are also polymers, alright. If they are polymers, then this means they are made up of some smaller units. And this smaller unit is what we call the nucleotides. The nucleotides are monomers. They come together to form a huge chain like what you saw in the protein. The same thing happens here, but these smaller units, they are not amino acids, they are rather called nucleotides. So nucleotides come together to form your nucleic acid. Your nucleic acid, we are having two main types. It's either it is DNA or it is RNA. You should know the difference between DNA and RNA by now. And also, there's a huge difference between the two in terms of how they are being produced, in terms of how they transmit information, in terms of how they manufacture proteins, in terms of how they store genetic informations. So this is a typical example of a sketch or an image that shows RNA versus DNA. RNA is usually single-stranded or it have only one strand. DNA is double-stranded. And we are having uracil in RNA, but instead of having uracil in DNA, it is being replaced with thymine. So for now, that's the difference between the two. And now let's move on. So let's move on to a very important topic. That is testing for the purity of organic compounds. So now we know what organic compounds are, right? We are saying that they are compounds that are made up of carbons. They contain carbons in them. That is organic compounds. And not all of them are organic compounds, even though they contain carbons. Example, if we are referring back, example is the oxides of carbons and also cyanides and also carbonates. Now let's move on. If you want to test for the purity of organic compound, if you want to check whether the organic compound that we are having is very pure, what can we do for you to check that it is pure? It doesn't contain any impurities. That is the definition of a pure substance. Now, the melting point of a substance is the temperature at which solid changes to liquid. So if you are having, let's say, sugar and you start boiling you start melting sugar, you apply heat to the sugar. The sugar is a solid compound, right? The moment you start seeing a liquid, meaning you are melting it. So melting and boiling, they involve application of heat, just that one involves transition from solid to liquid and the other one involves transition from liquid to gas. So the melting point of a substance is the temperature at which you are going to have your solid changing to liquid. and it is a key indicator of purity. The reason why we are going to look at it in terms of how we use the melting point to check whether this compound is pure or impure. And chemistry has made it very clear there are a lot of processes, experiments that have been taken to check for the melting point of compounds that is very pure. So when we are saying a compound is pure, that compound should have a sharp and reproducible melting point. This is to tell you that if let's say sugar, generally worldwide, if you're having sugar to melt at 80 degrees Celsius, then the sugar that you are having, if you want to check whether it is pure, after melting it or after you've applied heat to it and it is changing from solid to liquid, we expect that around 80 degrees Celsius, you should have your sugar melting. If the sugar is not melting around that 80 degrees Celsius, meaning if the sugar is melting below the melting point that you want, then this means that the sugar contains some impurities. It contains something that is not a sugar. For that matter, it is causing the melting point to be lowered. Do you get it? For instance, if you're having salt and you think that no, you see something and you realize that it's a sugar, but you are not sure whether it's a sugar or it's a salt, and you want to check the purity, you can try using the melting point. If you know that sugar melts at 80 degrees Celsius and you start melting it at 80 degrees Celsius, you should be expecting that the solid will be changing to liquid. But if you realize that the solid is changing to liquid around 70 degrees Celsius, then this means that it is not sugar alone. The sugar is impure. So the reason why, if you're having impurities or if you're having impure compound and you are using melting point method to check the purity, the melting point becomes lower is that, for instance, if you're having sugar, sugar is having a crystalline nature. But the moment you're having impurities in it, these impurities will disrupt or it will destroy the crystal structure of this salt or this sugar that you're having. Remember, it is the crystal structure that gives the compound the high melting point or its melting point that it is having. So the moment you're having impurities there, it disrupts or destroys the crystal structure. So you are going to have your melting point being lowered, or you're going to have a lower melting point. So instead of you having your sugar melting at 80 degrees, it's going to melt at around 70 degrees or lesser than that, because it contains impurities. And what did the impurity do? The impurity disrupted the crystal structure, hence lowering the melting point. Now, let's look at a term called recrystallization. So, after you've realized that your compound is impure, what can we do to make it pure? Or what can we do? How can we purify it? That is recrystallization. One of the processes is recrystallization. Recrystallization is used to purify a compound, and usually it's like 99% pure after using recrystallization method. Now, the impurities are being removed when you use recrystallization, and the melting point increases. So the melting point will then be restored and to be closer to the value that you are expecting the sugar to melt when it is pure. So melting range will become narrow again, and we are saying a narrow temperature range, meaning if your sugar melts at 80 degrees, meaning it is pure. If it melts around 79 degrees, the range from 79 to 80 is very small. It's narrow. For instance, example is what you are seeing here. A metal melts at 120 degrees Celsius to 120.8 degrees Celsius. You see the difference is 0.8 degrees Celsius. Yes, it means that the temperature range is very narrow. And when we are having a temperature range to be very narrow, it means that the compound is pure. So that's what is happening here in the recrystallization. That after you have used the recrystallization method, you are going to have your melting point increasing again because your crystalline structure will be restored. There will be no impurities to destroy it again, so it will be restored and your melting range will become narrow. So pure substance, this is a summary. The pure substance have sharp, high, and narrow melting points. For impure, its melting point to be lower, that is one, and also the range will also be high. Since it will be lowered, it will be, if you're having it to be boiling at 80, sorry, if you're having it to be melting at 80 degrees Celsius, then if there are impurities, it's going to melt around 60. So between 60 to 80, the range is very broad, suggesting that the compound is impure. Then purification, in conclusion, purification raises the melting point and also the sharpness range. It sharpens the range of the melting temperature. Now let's move on to the next one, which is the boiling point. But before that, let's talk about the melting range. The melting range, I've already discussed in the previous slides, that the melting range, it talks about two things here: the starting point and the ending point. The moment you start heating your metal and it gets to around 79.9, that is the starting point, because you are going to have your liquid starting to change to you're going to have your solid starting to change to liquid. So the starting point or the start point is the temperature at which your first drop of liquid appears, and the end point is the temperature at which every last solid crystal has what disappear. It means that the crystal has been destroyed completely. It has been changed to liquid, and that is what we are calling the melting range. Now, when you are doing these processes to check the purity, we are having irregularities that can occur. Sometimes the salt or the sugar, or let's say the compound we are melting, some of them are sensitive to heat. Sensitive to heat in a way that if you are melting it and it is being exposed to air, it can decompose before you even reach your melting point that you are expecting. It will decompose to give you another compound and a gas that will be evolved into the atmosphere. So to prevent these irregularities from happening, then it means that we have to melt it, or we have to melt the compound in a condition where we don't have air or oxygen there, because oxygen is the one that improves the decomposition of the compound if only it is sensitive. So if you want to do it, then this is that we have to make the reaction occur in a condition or environment that there is no air, because the composition can cause the compound to break down chemically. As you can see, it will also distort the melting point. The melting point that you'll be expecting, you are not going to get it, because after decomposition, the next compound that you are going to have will be having a different melting point than what you are expecting. A typical example is a calcium carbonate. If you expose calcium carbonate to air, it's going to decompose to give you calcium oxide. Right, this calcium oxide, it will be a metal, but if you are melting it, it's going to have a different temperature in ore. Calcium oxide and also carbon dioxide. This carbon dioxide is an air. It will be released into the atmosphere. What you are going to see is your your calcium oxide, and this calcium oxide will be having a different melting point compared to what you are looking out for. Now, for us to prevent this, we have to make the melting occur under vacuum. The vacuum is a condition, it's an inert atmosphere where it helps because you are going to have your oxidation be reduced. Oxidation is when your oxygen is being exposed to the compound. It undergoes oxidation reaction. This particular step is being reduced, so decomposition is likely not to occur. And with this, it will help you obtain a more accurate melting point because there is no decomposition. So this is an example of a vacuum space. This is a vacuum equipment. You can have your melting point occurring here. You suck all the oxygen or the air inside, and now you are going to have a vacuum. So no oxygen will be introduced for the decomposition to occur. Now, when we are talking about the boiling point method, the boiling point method is where you are going to have your liquid being changing to gas. So when you are having liquid changing to gas, there's a condition there. This is the condition. Boiling occurs only when the temperature at which the vapor pressure is equal to the atmospheric pressure. So when your temperature of the vapor pressure equals the external or atmospheric pressure, then this means that boiling is occurring. So when the temperature at which its vapor pressure is not equal to external pressure, boiling will not be occurring. But the moment you have your temperature of the vapor pressure equaling the atmospheric pressure, you are going to have a boiling occurring. And it's a physical property that is used to characterize new organic liquids. If you want to check that a compound is having, let's say, a boiling point, if you want to check that if you boil kerosene boils at 80 degrees Celsius, you can use boiling point method. And when you reach a stage where your temperature of the kerosene is equaling the temperature of the kerosene is equaling to the atmospheric pressure, meaning you are going to have the liquid kerosene evaporating to give you gaseous kerosene. So effect of impurities, unlike how we discussed about the melting point, and you realize that in terms of melting point, if you're having impurities, it's lowest. As for boiling point, it's not all that sensitive to impurities. So meaning if you want to check out for the purity of a compound, usually you don't have to rely on the boiling point, because the boiling point will fail you sometimes, because impurities are not sensitive to boiling point. It's only melting point. So now let's move on to something very important here. The factors that affect boiling point. If you are boiling something, let's say you are boiling water, you know that water boils at 100 degrees Celsius. But some conditions can make water boil at 105 degrees Celsius. There's other conditions can also make the same water boils at 80 degrees Celsius, 60 degrees Celsius, 90 degrees Celsius. They are conditions. So factors that affect boiling point. If you want to check water boiling at 100 degrees Celsius, you have to maintain some conditions. One, atmospheric pressure. But in this case, let me use this one as an example. If you are on a mountain, if you are on a mountain and another person too is also at the bottom of the mountain, if the two of you are boiling the same water, the person who will be at the valley or who will be at the bottom of the mountain will be reaching a temperature of, let's say, 105 before you are going to have your water boiling. But the person who is on top of the mountain will take like less than 105. The person will take like, let's say, 90 degrees, then the water will start boiling. The reason arises from atmospheric pressure. At the top of the mountain, atmospheric pressure is very minimal. But at the bottom, atmospheric pressure is very high. The greater the atmospheric pressure, the greater the boiling point. And the lesser the atmospheric pressure, the lesser the boiling point. It's very simple. This trend is very simple. So you could see here that boiling point decreases by 0.5 degrees Celsius. The word here is decreases. So it decreases by 0.5 degrees Celsius every 10 millimeter decrease in atmospheric pressure. So you can see that decrease in atmospheric pressure relates to decrease in boiling point, like I said earlier. The second one is molecular weight. For the molecular weight, I can use kerosene and coal tar, for instance. If you're having coal tar, a container containing coal tar, you know how thick is it? Very dark and thick. And you are having kerosene, light one, of course. If you are boiling these two, you are going to have kerosene boiling faster. Let's say around 80 degrees Celsius, kerosene will boil faster. But around 600 degrees Celsius, that's when you are going to have your bitumen. You are going to have kerosene, you are going to have your coal tar or your bitumen boiling. So this is to tell you, in terms of the molecular weight, coal tar is heavy as compared to kerosene. So the greater the molecular weight, the higher the boiling point, because there is something called intermolecular forces. And per my example I've given here, the forces that exist in these compounds are referred to as van der Waals forces. Whilst we delve into the course, we are going to talk more on van der Waals forces. We are going to talk more on other forces, whether intramolecular forces or intermolecular forces. So now let's move on to the next. If you are using melting point and boiling point, let's look out for the effects. In terms of impurities, impurities lowers the melting point of a substance. But when you're having impurities, impurities will raise the melting point of a liquid. So if you are having kerosene boiling at 80 degrees Celsius, and then if this is kerosene, pure kerosene, it boils at 80 degrees Celsius, and then you are having another container, a dirty container of which you have poured your kerosene inside, you reach 80 degrees and you still not seeing your kerosene boiling, maybe around 120 degrees before you have your kerosene boiling. That is it. It means impurities raises or increase the boiling point of a liquid, but impurities lowers the melting point of a substance. I'm using substance here because melting is from solid to liquid, whilst boiling is from liquid to gas. So now let's look at the reason. This is the reason, like I always say, the reason is that impurities would disturb the regular structure of the molecules in solids and changes the intermolecular interaction, the forces that holds these molecules together for it to have that melting point. If you're having impurities there, it's going to destroy the forces. It's going to change the intermolecular forces. And if it is being changed, the only thing that is going to happen is that it's going to disrupt the melting point as well. The regular melting point that you want, you are not going to get it. So a pure substance will be having a sharp, constant melting point, but impure substances will melt over the range of temperatures. It will melt, it will not be in the range of temperature that you are expecting because of the impurities. And also it will boil over a range of temperature. It does not maintain a constant temperature. Meaning if you are having impure kerosene, at a point you are having it boiling at 120 degrees. The next moment you are having it boiling at 110. It doesn't contain or it doesn't maintain a constant temperature during the phase of change. So now there's a next method, which is the refractive index. The refractive index will describe how a beam of light will bend. So when you are having a glass beam or a glass prism, if this is your glass prism and light passes through it, this glass it's moving from a less dense medium to a more dense medium, so it's going to diffract a little and now it will move again. You get it? So there's going to be a change in light pattern. So the cause of refraction, if the refraction occurs due to a change in speed, the moment you are going to have the light passing through this medium, the speed is going to change. And if the speed changes, it bends. So this one is related to physics, right? And there's a formula that is used to find the refractive index, represented as n, as you can see. And this is the formula where this particular sign is your angle of incidence and this is your angle of refraction. Here is the incidence, angle of incidence, and the angle of refraction is this, as you can see here. That's what you can use to find your refractive index, so the sign of the values. Or you can also use a method like the velocity. If you can calculate for the velocity in the medium and also the velocity in the vacuum, you can also calculate for your refractive index because they are related to the angles. Now there is a next example, very interesting. This next example is called the thin layer chromatography. So let me give you a brief idea about what a thin layer chromatography is. So if you have realized back in basic schools, grade A schools, if you have an ink pouring on a paper and this paper is being soaked in water, for instance, at some point you are going to realize that the ink has been patched. You are going to have patches of the ink with different colors on that paper. That's a typical example of thin layer chromatography. So the principle is that thin layer chromatography is a technique that is used to separate and identify components of a mixture based on their movement on a stationary phase. So when we are talking about stationary phase and mobile phase, we'll be delving more into it. Components of a thin layer chromatography. Here we are talking about thin layer. So let me give you a typical example. Let's say our layer here is paper. The paper is the stationary phase, but the mobile phase is the water that poured on it. If you have a tissue and you soak a tissue in a paper, you are going to have the water sorry, if you have your tissue and you soak it in water, you are going to have the water climbing by capillary action. The water is going to climb up the tissue. The same thing happens here. So your water becomes your mobile phase, and your stationary phase will be the paper. So the same thing applies here, but in thin layer chromatography, the paper that we are using is silica gel or alumina. Now, the alumina is just a foil that has been coated with a layer. So it is on this layer that you are going to have your solvent moving through. So let's see an example here, how it works. If you are having your water, for instance, and you dip, let's say you spot your ink here, and you dip this ink together with the paper into this particular solvent, you are going to have your water starting to move up. So when it starts moving up and it reaches this point, let's say the water has climbed through capillary action up to this point, you are not going to have your ink still being there. Your ink is also going to move up whilst the water also climbs. Meaning, if you are having different components, if the ink is impure, let's say if the ink is made up of color red, color blue, color black, all mixed up, it means that whilst the water moves up, you are going to have color red separating from color black and color blue separating from, let's say, the other colors. That's how thin layer chromatography works. So the different components in the mixture, they will move at different speed. Like you are going to see, you are going to have blue, let's say, traveling a little bit slower. Red will be traveling faster than blue. Violet will be traveling faster than all of them. That's how it is. They are going to travel at different speed. The reason why they are going to travel at different speed is that, one, their solubility. If you're having red in there, if you're having blue, if you're having violet, they are going to travel at different speed based on their solubility. Are they soluble in the solvent? If color red is soluble in the solvent, then this means that they like the solvent. So while the solvent is moving up, they are moving up with the solvent. So they'll be traveling faster. In case of, let's say, this color, if you're having this color here, as you can see with the arrow, this color is not moving fast enough. This means that this color is being attracted to the paper more. It is not soluble in the solvent as how this particular one is soluble in the solvent. It's rather interacting with the paper, and the paper is the stationary phase. So the ability of components to move, their difference in their speed arises from, one, solubility in the solvent, or the affinity of the component to interact with the solvent, and two, interactions with the stationary phase. Okay, so this is a typical example of what I was saying. This is what it has been done in most laboratories where you are having your thin layer. So this is your thin layer paper or your alumina or your silica gel. So this is it, the white one. Before you start your experiment, you have to make a line here. So this is the line that we made, and it's on this line in the middle is where we place our spots. Let's say our black ink. This is where we placed it. So the moment, and in this beaker or in this flask, we are having the solvent there. So the solvent can be alcohol, it can be ethanol, or it can be, let's say, a non-polar solvent, right? Now, you have to know the characteristics of the solvent. The moment you dip this particular TLC paper into the solvent, you are going to have the solvent climbing up by capillary action. So when it starts climbing up, we are going to have the colors separating. So you can see that the ink that was here was having green components there, it was having blue components, it was having something like a violet here, and it's having something like an orange here. So you see they are all traveling, but when they are traveling, they are moving at different speed. That is thin layer chromatography. Now, if you want to visualize it, these are the methods that are being used in visualizing the spot. The first one is the iodine chamber method. And with this one, you are going to perform a lot of experiments in the laboratory. That will let you understand the iodine chamber. The TLC paper is placed in a sealed jar containing iodine. So the iodine vapor will then react with the organic compound and it will form an irreversible complex. This reversible complex is the one that makes the spots visible for you to see. Now the second one is the UV light method. Some of the spots are there. You can only spot it when you sorry, you can only spot it when you interact it with, let's say, a UV active fluorescent indicators. Now let's move on to a very important note here. Now the note that I'm supposed to have is separation depends on the interaction with the solute, stationary phase, and the solvent. So for you to have your components separating, it depends on the ability of the components in the mixture to interact with the stationary phase and also interact with the solvent. If you are having a component interacting more with the stationary phase, it means that it will not be traveling faster. But if you are having a component traveling faster, this means that it is soluble in the solvent or it is interacting more with the solvent as compared to the stationary phase. Iodine staining is reversible and general for many organic compounds. So when you are doing your thin layer chromatography experiments, you can use the iodine staining because for that one it is reversible. You can spot it very easily and it is very general for many organic compounds. The UV method is used for UV active compounds. Some of the compounds are there. You can only use UV light to spot them. So even though you can see it traveling, if you don't relate it or if you don't subject it to UV method or UV active light, there is no way you are going to see the spots and you can't find your RF value. RF value is a property of chromatography. It determines whether the compound is traveling faster or not. We are going to look at it in a few slides. So elution characteristics, that's the same thing as the RF value. Now, the movement of a compound on a TCl plate is expressed using RF value. RF means retention factor, so retention factor value. Now, it shows how a substance travels as compared to the solvent front. Let me show you a typical example of what I mean by a solvent front. When you are having your TLC paper and you soak it in the solvent and now your liquid starts rising up, the level that it will reach before you remove the TLC paper, that particular level or that line is what you are referring to as the solvent front. That is the maximum distance that it has traveled to. So you could see that is the denominator. So if you want to find RF value, and let's say you place a dark spot here. So now the dark spot has been separated into 8 components, component A and component B. So this is component A and this is component B. Now, component A is having RF value. Component B is also having RF value. This is how we find the RF value. When you make your distance here, so you have to make a line like I said always, and you put your ink there. So this is where the ink started traveling. And this is where the solvent reached before you remove the TLC paper. If you want to find RF value for A, then RF value for A will be equal to your denominator will be the distance from this particular solvent front up to this line. So let's say the distance that it traveled by the solvent front. Let's say this distance is 20 centimeters. Then this means that your denominator will be 20 centimeters. And now, since you are finding the RF value of compound A, we have to find the distance from compound A, the distance that was being traveled by compound A. So that one too, let's say, and let me give you a very caution here. there is no way you are going to have your compounds traveling faster than the solvent front. As in, there is no way you are going to have your RF value greater than 1. So to be 20 centimeters divided by the distance that was traveled by A. So let's say the distance traveled by A is 10. So you are going to have 10 divided by 20, and we are going to have 0.5. Let's do the same thing for B. I'm finding it difficult writing because I'm using the mouse pad. So 0.5. Now let's do the same thing for B. So B, the solvent front distance will also be 20 as usual. And for B, you could see that B has traveled a little bit longer, closer to the solvent front. So let's say this one is 18. Then this means that we have our RF value for B to be 0.9. Then this should give you idea that if you are having a greater RF value for a compound, meaning it travels faster, it was interacting with the solvent more. You get the concept? If the RF value is bigger, then this means that it has traveled faster, because see where B is, it has traveled faster and its RF value is 0.9. But if it travels slower, like A, you could see that the RF value is smaller. So the greater the RF value, the greater the interaction of the compound with the solvent as compared to the stationary phase, meaning it interacts with the solvent more than the stationary phase. And like I always say, there is no way you are going to have your RF value greater than 1. Like you are having your color at this particular point where the solvent has not even got into. It's not real. It's invalid. So there's no way you are going to have your R to be greater than 1. R can be closer to 1. R can be equal to 1, alright. Then if R is equal to 1, then this means that, so let's have a compound C. If compound C is here, then this means that the distance traveled by compound C will also be 20, and 20 divided by 20 is 1. Meaning the compound is interacting with the solvent alone. It's not interacting with the stationary phase, so it is not slowing down. Now the purity check, I've already described it to you. If this is your TLC plate, and you make your line and you perform your chromatographic experiment, the moment you start having more than one component there, you start seeing red color and blue color somewhere, it means that the substance is not pure. The ink that you're having here is not pure. It's not made up of only one thing. It's made up of different components. So it's impure. But the moment you do your chromatographic experiment, chromatographic experiment, and then you are having only one spot after dipping it into the solvent, you realize that it's only one spot, it's only one black spot that you are seeing throughout. Then this is to tell you that the compound is pure, because a pure substance is made up of only one spot on a TLC plate. But an impure substance, you are going to see multiple. For instance, let's look at this image. Let me clear this part. So you could see that this is the initial part of the experiment. After we have dipped it into the solvent, now we are seeing different colors like color 1, color 2, color 3. It means that this particular spot that you made here, the compound is impure. But the moment you dip it here, and it's only one black spot it's only one spot that has been moved throughout on the TLC plate, then this means that the TLC plate is a pure, or it means that the compound is a pure substance. It's not made up of any other thing. So now this brings us to the end of lesson 1. Now, the next lesson will be purification method. And we are talking about purification method. What do you mean by purification method? After you've realized that the compound is impure, what are the things that we can do to make sure that the compound becomes pure? Its melting point and boiling point is being restored. Now, for more information, I'll be ending the lessons here. So for more information or assistance, you can email me or you can call me through this particular contact. And also you can join my Telegram premium channel for in-person or online tutorials. Remember, this one, it teaches you a lot of things that will not be taught even at lectures into details. And also we are going to talk more with animations and things that will help you understand everything into details. You'll be solving more questions as time goes on. So make sure you stay tuned and subscribe to the channel, like, and also comment on the video. Thank you, and I'll be seeing you very soon. So the next lesson will also involve, so this is an image of my Telegram premium my premium Telegram channel where I teach a lot. So you also be, after the purification methods, we are going to talk about qualitative analysis of organic compounds, how to determine the empirical formula, how to determine the molecular formula. So by joining the Telegram page, it's going to help you because the next lesson will focus on qualitative analysis of organic compounds. And before we begin, selected practical questions will be solved into details all on this Telegram premium channel. And also for the last, if you are having any issue, if you want assistance, if you need help, you can also email me or contact me. I'll be seeing you soon, and I'll be willing to assist everyone who needs help in organic chemistry. Bye.